So let me first go through that the Lyapunov exponent first, then I will show you some example. So by we have so far learned that but to see that whether or not a dynamical system has some chaotic component in it or not, we can draw a can draw a orbit diagram, and from that orbit diagram we can surely say that there is something which is aperiodic, but to, to say something about that chaos we need one thing, that is sensitive dependence of the initial condition, or which is known in in the another familiar term, more familiar term, which is butterfly effect. So to know that whether or not the system has that component that is more crucial for called that thing a chaos, so that is the sensitive dependence of the initial conditions. So is there any method that to measure that there is a sensitive dependence of the initial condition? And we have learned in the previous class that yes, indeed there is a method which is called the Lyapunov exponent. And Lyapunov exponent characterized that the thing that how fast system, how far too closely, suppose there are two very closely remain initial conditions, and Lyapunov exponent says that how fast they are going far apart. If we assume that these two initial condition with time, that means with iteration, goes from one another exponentially, then we can suppose that delta n is equal to delta 0 exponential to the power lambda n. So if we assume that the distance from these two initial condition, if we iterate both of these two initial condition n times, then the distance will become delta n. So then this delta n, as if it is going, as if delta 0, this initial conditions, the slightest difference of the initial condition goes exponentially, and we developed a method to calculate this lambda. So lambda, basically from here you can calculate that lambda is basically 1 by n ln delta n by delta 0. So from that, by numerical algebra, by algebraic jugglery, we have shown that lambda equal to 1 by n ln f n first derivative of fn at that fixed point or x0, so that will give us the lambda. So exact value of the lambda is limit n tends to infinity 1 by n ln fn is first derivative at x0. Now for our previously we have seen that this fn prime can be written as a multiplicative series. So we know that the f square x could be written as f prime x0 and f prime x1, where x1 is f of x, where x1 is f of x0. So in this similar manner we can write this also as a multiplicative series. So from there will be n, here f square means 2 multiplication, here there similarly there will be n multiplication. First will be f prime x0, then f prime x1, then x2, x3, x4, and up to the multiplication will be f prime x n minus 1. So that's how. So and we know that there is a one rule that logarithmic of any multiplication will become the summation. So that's why this logarithmic of this fn x0, and which could be write as this multiplication series, that becomes the summation limit 1 by n I equal to 1 to n minus 1 ln f prime x0. So that is the, so let me write it clearly here. So limit n tends to infinity 1 by n I equal to 0 to n minus 1 ln f prime xi. So that is the basically definition of the Lyapunov exponent. And what is this xi? Xi will be that f of x of I minus 1. So in the similar manner, from the x0 you will get x1, and from the x1 you will get x2. So that's how we'll generate this xi. And the f prime, if actually if you know the function, the map or the function, you will get the first derivative. So that is how the Lyapunov exponent. Now what happens? So first of all, by looking it, you can see that this lambda actually seems that lambda is dependent on the initial conditions. So from which we have start? Here we have start from x0. Now if I start from the question, if I start from any other initial condition other than x0, will it be different? No, it will not be different. If we know that all the initial conditions are going to a same fixed point, suppose so that is called the basin of attraction. So suppose there is a one initial condition in x axis, one initial condition, suppose this is x0, and there is one fixed point here sitting somewhere. Now if all the initial conditions, suppose this to this, all the initial condition belongs to in between these two brackets are going to this fixed point, then we say that the set of initial conditions, or from this to this point, this is called the basin of attraction of this fixed point, suppose x star. So if all the initial conditions are going to a same fixed point, then the Lyapunov exponent for those all initial condition will remain same. Basically I am saying that if I taking initial condition this or this, it doesn't matter. If both of the initial condition goes to this x star, the Lyapunov exponent will remain same, because you see we are taking the limit n tends to infinity. We know that if I iterate it infinite time, it ultimately go toward this fixed point. So after a few iteration, it will be very nearer to x0. So when it will be very nearer to x0, all the initial condition will the previous few iteration will contribute very few, but the iteration will be remain very close to x0 will give a lot of strength in that summation. So that's why all the initial conditions which go to a single fixed point, or technically it is called all the initial condition from the basin of attractions will give the same Lyapunov exponent. So this is how we calculate the Lyapunov exponent, or we actually tell whether the system contains any kind of butterfly effect or not. So if how we will tell? So first of all we calculate lambda. Now how we can say that whether or not system has a initial sensitive dependence of the initial condition? Similarly, so from this logic, if these delta n from delta n grows as n increases, as time increases or iteration increases exponentially, then we can say yes, the system has a exponential growth. So then that means if sensitive dependence, and this is equivalent to lambda greater than 0. If lambda greater than 0, now let's put it here that delta n will be delta 0 exponentially n lambda. If lambda greater than 0, they will increase exponentially. So the graph will be look like this. So from here they will exponentially grow like this. So that's it. Now suppose that this is lambda is less than 0. So if lambda is less than 0, that means delta n equal to delta 0 exponentially minus n something, some constant lambda 0. So lambda equal to, suppose that, minus lambda 0. So it is a negative quantity. Then you see, as time increases, the distance between the two initial conditions will shrink or will decrease and decrease, and there they will go to 0 as n increase. So it will look like this. So first of all start from delta 0, then it will continuously decrease and it will some point, so this is increasing n, so at some point it will become 0. So that means, so the any difference between the two initial condition will not remain. So this is a very powerful technique for any scientific measurable quantity. So you see, as we have discussed in the previous classes, that we cannot say exact initial condition because of our instrumental error, or for the basic, there is the structure of the real numbers, because the real numbers contains infinite set of irrational number, and since irrational number cannot be written precisely, so that's why we cannot precisely give any initial conditions. So if I cannot give any precisely initial condition, you see that means I am giving, suppose my exact initial condition is delta 0, suppose my population density at today is x0, but I can only give, or the cell density of the cancer cell at this point is x0, and its actual value remains very close to x0. It's not exactly close to 0, its real value may be x0 plus delta 0. Now the question is, will my future, if I predict the future from our theory, will it match toward the reality? Yes, indeed. If it will matches with reality, if the lambda is less than 0, if there is no chaos. So if there is no chaos, we know that with time the discrepancy between these two things will die out eventually, and will get the real results. But if this lambda greater than 0, then it will become very horrible to us, because our theoretical prediction will not matches with reality, because these small deviation from the small deviation which we are not capable to give as an initial condition, it will grow the discrepancy from the real world results, reality, and our theoretical prediction will diverge away. So this is called the sensitive dependence on initial condition, and it is called the, so that means we have to prove that the logistic equation, that we are saying that when the orbit diagram become very dense, there is chaos. So we have to prove that. So we will prove in this lecture. So let's see another thing. Example. So first example. Yeah. Okay. Say. Yes. Okay, they exponentially. Could you repeat it? Because I think that what you want to say, that that the difference between the two initial conditions, suppose you are taking two very close initial conditions, that their difference between that two initial conditions is very slight. Now if we iterate, or if you iterate means if you just measure it through every minute, or if you iterate by the map, with the time or with the iterations, these two initial conditions will exponentially apart from each other. So that's it. Now let me give you an example. Suppose that f sub function f has a stable p cycle containing point x0. Now we have to calculate the Lyapunov exponent. What is the Lyapunov exponent? So from our previous discussion, we can safely say that the Lyapunov exponent should come negative, because the stable p cycle is stable. That means all the initial condition will eventually go towards that attractor. So if they all go towards eventually a same attractor, that means any initial condition I take, their ultimate fate is the same thing, that oscillating thing. So if all the initial condition will go toward the oscillating thing, that means all the initial conditions with time, their distance between the two initial conditions will decrease to 0, and ultimately they will fall to p cycle. That means the lambda should come 0, less than 0. So let's see, so whether or not it is less than 0. So what we know? That means if f has a stable p cycle which contain x0, that means this x0 is a fixed point. X0 is a fixed point of fp. If I iterate p times x0, it will return to x0. So if I that means it's a fixed point and it is stable. What does we know? What does the stability means? So this is the existence of the p cycle orbit. Now what does stability mean? Stability means we know that since it is stable, so that means if I derivative if t dx of fpx at x0, it will be less than 1. It will be less than 1. That we know. That means stable. That stability does mean. Okay. So this could be right as. Now if this means this can be right as fp prime x0 less than 1. So if I take ln both sides, logarithmic ln, so if p prime x0 less than ln 1, so this will be ln f prime x0 less than 0. Logarithmic 1 means 0. So that we gonna use. Another thing, what is the definition of the Lyapunov exponent? Lyapunov exponent means limit n tends to infinity 1 by n ln summation I equal to 0 to n minus 1 f of f prime xi. Right. Now you see that if you take any initial condition, what is ultimate fate? So if I iterate this infinite time, so ultimately it go towards, suppose this is p orbits, so it will eventually hit to this p orbit and they will oscillate between the p orbit, these p points. So from x1 to x2, x2 to x3, x1 to x2, x2 to x3, and at last they will hit this xp. So at last it will go xp, and if I iterate again from xp to, it will go again x1. So this p point will appear multiple times, means infinite times. So this group of these p points will appear multiple times. So instead of this n, we can write, so there are only p iterations. So after p iterations, it will again p plus 1 iteration will be same as x1. So n can be written as, suppose p iteration into some constant k, some value k, p is the period of that thing. So if I put this, so this is equivalent means k tends to infinity 1 by kp. This is summation of ln, and this will be I equal to I equal to 0 to p minus 1. So p point will be the same. So okay, let me write it in this way, kp minus 1 f of a prime of xi. So you see there are kp points. So kp, between the kp point, we know that the the group of p points appears k time. So that's why it is kp point. So this is 0th, suppose 0th point x0, this is x0, this is x1, this is x2. That's how this is x kp minus 1, and that means this is all together kp points. So number of kp points, and out of number of kp points, we know that every p points are same. So these group of point appears here k times. So that's why we can take it out. So I think I am wrong here. So this summation will not be the inside. Okay, previously I have written it wrong, maybe. The summation was outside the ln. So there was a wrong. So summation is actually this I equal to 0 to n minus 1 ln this. So summation will be a prime xi I equal to 0 to kp minus 1. So this will be, so this chunk will appear kp times, so k times. So this means this will be k times I equal to 0 to p minus 1. So this is p point. So here don't worry, here I start from x1, that's why it goes to xp. Since I am starting from x0, that's why it goes to kp minus 1. So I have added here one point, which is x0, that's why I have to remove this point, and this means xp minus 1 is here. So that is ln f prime xi. Now you see this is cancelled. So that means limit k tends to infinity 1 by p 0 to p minus 1 ln f prime xi. And we know, so and this is k tends to infinity because there is no k, so we can get rid of this limit, so it doesn't require here. Now This means we know that the summation of this logarithmic can be written as the multiplication. So 1 by p ln multiplication of I equal to 0 to p minus 1 f prime xi. And what do we know? That f p prime x0 can be written as xi equal to 0 to p minus 1 f prime xi. So this could be written as 1 by p ln f p prime x0, and we know that f p prime x0 is less than 0. So that means this is, since 1 by p, since this p is greater than 0 and this is a negative term, this is a positive term, so this in positive term into negative term should be a negative term, so this is less than 0. So yes, indeed, so for a stable p cycle it is appearing that the lambda, this Lyapunov exponent, is negative. Is it clear, Subhaji? Okay. Right, exactly. That's why, yeah, stable p cycle. Exactly. Now another example, let's give me another example, then I will go to the logistic equation. So another example is fx is equal to rx, where x is 0 to less than half and r minus rx of half greater than x less than equal to 1. So this is called the tent map. So this will be, so up to half, that is the up to half, so this is going to like this, and it reaches to r by 2, sorry, it reaches to at half, it reaches to r by 2, this is r by 2, then from r by 2 to it reaches to 0 somewhere here. So this kind of tent map is this kind of graph. This is xn, this will be xn plus 1. This is tent map. Now if I ask you to calculate the Lyapunov exponent, so what should we do first? First we have to do the derivative first. So let's derivative it. So f prime x, you see f prime x actually does not depend on the value of x, from where we are starting it doesn't depend at all, means so if I f prime, the first derivative of f, its value is r if x remains between 0 x less than equal to half and equal to r minus r, it remains half x less than equal to 1. So the modulus of f prime x, although the f prime x depends on the x, whether or not x is remain between less than half or 0, then the slope of this curve is positive part, and if it will remain in this side, then the slope of the curve is negative. So that is saying f prime x. So f prime x modulus of f prime x will be r. So that will not depend with the initial conditions value x0. So now if you calculate the lambda Lyapunov exponent means, so limit n tends to infinity 1 by n summation I equal to 0 to n minus n ln f prime xi this is so we know that any f prime xi is r. So limit n tends to infinity 1 by n, this is summation of I equal to 0 to n minus 1, this is ln r. So that means this is n times ln r. So this is limit n tends to infinity 1 by n into n ln r. So this is only ln r. So lambda we get ln r for the TED map. So from here we can see one thing, that this TED map will be when the lambda will be less than 0. Lambda less than 0 means r less than 1. So that means for a TED map r less than 1, the system will not be chaotic, and if lambda greater than 0, that means r should be greater than 1, then it is chaotic. So that's it. Now this is very simple example to do, but in reality the problem is that most of these cases you cannot do algebraically by your hand. You have to use numerical method, or you have to use the computer to calculate this Lyapunov exponent. As for example, the logistic equation that we are studying here. So if I want to see what is the value of lambda, what is the value of lambda if I increase r. Okay, if I increase r, what is the value of lambda? So for that, what we do? So we have to since we know that logistic map is xn plus 1 is r into xn into 1 minus xn. So it is very complicated, and it means since there is a very simple and straightforward, that's why you can do by it this way, but actually you can't do it that way for every map. So you need a computer. So how to do it? First, what you will do, so the steps are, so first you take a single values of r, and any random initial condition. Suppose any random initial condition, then you iterate this random initial condition. Suppose n prime is 300 times, suppose 300 times or something, 300 times. So it doesn't matter whether or not you are taking 300 times, but you suppose instead of 300 times you 345 or anything. The thing is, you iterate for some longer times to die out its transient behavior. That means let the initial condition to closer to this fixed point or anything closer to the fixed attractor. So that's why you are otherwise what will happen, if it suppose there is a stable attractor, but since you are not giving him enough time to goes the transient behavior, that's why you are seeing the lambda greater than 0, but it is actually not lambda greater than 0, it is transient behavior. So that's why you have to first of all iterate for sometimes sometimes then you will get some, suppose x n prime. You iterate this n prime times, that's then you will get a value x n prime. Now third step is, from the third, what you will do, since you get this x prime, then you can calculate the f prime, first derivative of fx, first derivative of f of x at this point. Take the modulus value of that and take logarithmic, and suppose take logarithmic this. Now repeat this third step, repeat. Suppose now what you do, again iterate this n prime, suppose then n prime plus 1, then you will get what, you x n prime plus 1, you will calculate the same thing, ln dx of f of x, f prime n plus 1, first of n prime 1. Now you do the same thing, you iterate again, you will get and do this thing, so, and you will get these thing and these things, all the things, so you add these things. So after iterating this, what you will do, then you will do that, suppose this is d0, suppose this is d1, d0 d1, so you add d0 plus d1. So or you can repeat this step, suppose a large number of times n prime plus 1, then you will get x n prime plus n, that, and from there you will get d capital N, that is ln t dx of f of x, that is x prime n plus n. Now you see these points, you get d0 d1 dn, and n should be very large. Suppose if you take n prime 300, let's take n equal to 10,000, and then what you will get, that the Lyapunov exponent is basically the average of these things. If you see the definition of the Lyapunov exponents, y1 by n, I equal to 0 to n minus 1 ln f prime of xi. So this is are nothing but this is the f prime of that xi. So that means if we add these all the things, so 1 by n d0, this modulus of it I equal to 0 to suppose n di. If you add those things, so it should be n plus 1, so n means n plus 1, so here no, then it should not be this d1, this be second term, so this will not be dn, this will be dn minus 1, okay, something like that, okay. This is dn minus 1, so you will get this lambda. So that's how you will get the Lyapunov exponent. Is it clear? Every step is clear? Subhasaji? Okay, yeah. Then okay. So let's see the example. So I have written a code for where it actually generates these things. So let's go step by step here again, then it will be maybe clear. So what happens, so let's see here. So what we are doing here, first of all, so what this is, I means it is, this is in Python code, this is called iteration. So every iterations, computer what you will do that it will increase the values of I by 1. So that means it goes the iteration. So here this is the, suppose this is the iteration that I'm talking about, that every time it iterates. This is the logistic equation. Now I am saying that if I greater than that, here I have taken that that transient period is 5,000. So if greater than that, if it greater than 5000, so after 5000 iteration, what I will do, I will calculate the derivative. I will calculating the derivative, and derivative of that f of x we know. Suppose we calculate the derivative, so fx, if fx is r into x into 1 minus x, so r x minus x square, so f prime x will be r into 1 minus 2x, so that will be r minus 2 into r into x. So after 500 I am calculating that every derivative, that r minus 2 into r into x, and I am taking that absolute value of that thing, and what I am doing, that I am adding to that d1, adding that value to the previous value. And after doing all these things, I am, let me plot, I am plotting these r values versus this lambda by the last iteration, last 5000 iteration I gonna iterate. So let's see what is showing. So let's see, and I am also here also plot this orbit diagram to show you there is a chaos when lambda greater than 1. Let's see. Yes, now you can see from here. My computer is lagging. Okay, now can you see this figure? So this below this panel, in the lower side panel, you see the Lyapunov exponent. Now you see where the 2 cycle appears. This is 2. I have said that this is the 2 cycle period. This is because there are orbit diagram, there are only 2 points are there. So the ultimately at infinity, the point will be oscillating between these 2 points, and you see the Lyapunov, this is the Lyapunov exponent graph, this is Lyapunov exponent, and this is the orbit diagram. So when the orbit is stable 2 cycle, you see negative and negative increases and goes to infinity. So somewhere between here it goes to infinity, negative infinity, and when it goes to negative infinity, that is called, let me one thing remind here, when lambda goes to infinity, that is called super stable cycle. Since lambda is the signature of the stability, that's when lambda goes to infinity, minus infinity, it is called super stable fixed point or super stable attractor. When it goes to super stable, so you see that f prime x will become 0, where f prime x will become 0, 1 minus 2x, it will become 0 at x equal to half. And we know that ln f prime x or equal to ln 0 means ln exponentially minus infinity. So this means ln 0 means minus infinity. So whenever the fixed point, any fixed point of the any of the one fixed point of the stable attractor, any of the fixed point of the stable attractor become x equal to half. So if any point of the stable attractor is x equal to half, that means that attractor is super stable. So here you see, so when if you draw it here, so you see that infinity, so this is lower point, is actually at 0.5. This is 0.4, this is 0.6, so it is 0.5, exactly 0.5. If I draw, I didn't draw a line, so if I draw a line where this infinity goes, you will see that it exactly cuts this lower half at 0.5. so that's first of all, this negative infinity signifies that. Now the interesting point is there, first this negative point, then there is a period double bifurcation, and when the period doubling bifurcation occurs, you see one signature, the lambda becomes 0. So that means whenever the bifurcation occurs, then the Lyapunov exponent will become 0. Now whenever it goes here, then here the first times when it goes to positive, where this there I draw a red line, and this red line is r infinity, where the by the period doubling route, that infinite periodic orbit appears, then it loses stability. So that is indicated with red lines, and you see from the red line in the orbit diagram a dense point started, and here also from this red line, after the red line, that Lyapunov exponent start to become positive, and in between you will see, in between there are some spike which is goes in the negative direction. Those are the periodic window in between. And other where the Lyapunov exponent is greater than 0, then you can see the orbit is very orbit diagram shows very dense picture, and this dense picture means chaos. So simple, here you see the periodic window is negative negative spike. Here also you see whenever at the starting point of the stable 3 cycle, you also see that from chaos to it suddenly decreases to 0, and it goes through a bifurcation. It is, we know that this is a saddle node bifurcation, and it becomes negative, and that means it becomes stable, and the stable 3 cycle, and it gives birth of this stable 3 cycle, and again by the period doubling bifurcation it goes from 0 to again positive, and it goes on. So that's how it is. That's how Lyapunov exponent, that's how shows the exact behavior of the chaotic attractor and the chaos and the stable attractor. So that's all. Is it clear, Sobusaji? Now oh, that's a Lyapunov diagram. That's, I am drawing the Lyapunov exponent with R. Okay, let me show you. Okay. So sorry for I didn't give the leveling, y-axis leveling. I should give the y-axis leveling. This is nothing but this is lambda. This is the lambda I am plotting. Lambda versus r. This is Lyapunov exponent versus r. Second diagram, the second column, second row diagram. That's the Lyapunov exponent diagram. So I am generating the Lyapunov exponent with r with the help of computer. The step I have shown you there. So I am just, by computer programming, I am just following those steps blindly, and I am generating this Lyapunov exponent diagram. So at any point, suppose r equal to 3.2, what is the value of the Lyapunov exponent? That is this value. At suppose here, what is the value of Lyapunov exponent? That is negative infinity like thing. So is it clear, Subhaji? Okay. Okay, then I will go toward another thing that is called the universality. So it is clear that let's go toward the universality. Universality. So whatever we have seen here, is it only only true for this logistic equation? xn plus 1 equal to xr xn 1 minus xn. Is it only true with the logistic equation? If I take any other equation which goes through this goes to chaos through period doubling route, will not be will be there something same in between these two, or these two will be completely different? That means, can we say something general about the period doubling bifurcation itself? Not it is means, can we say there is something that is the property of the period doubling bifurcation, not the property of the logistic equation? If I, instead of logistic equation, suppose I am taking these equations, suppose xn plus 1 equal to some complicated equation, let's take it, sub r sine pi xn, and here r suppose below 0 to 1 and x belong to 0 to 1. Suppose if I take this and it goes to chaos through the period doubling route, there will be something that will similar to the logistic equation. So that is the universality, that is saying that some property will be there that will be universal to the period doubling root of chaos, not the property of this map. So it is will say that it will be not property of this logistic map or this complicated looking map. It is the property of that fact that the system goes to the period doubling chaos through period doubling bifurcation. So to see that, first let us see this map. The similarly here, the orbit diagram and the Lyapunov exponent. First of all, the orbit diagram, and the second Lyapunov exponent for this this sinusoidal curve. So from r minimum, so on, suppose 0.7 to 0.7 to suppose 1.0. Here this will be simply this is r into okay, let me write it in this way. Okay, let me x equal to r x equal to r into so Bhusaji, do you know anything about the Python? Okay. Material is so I have seen some there are a lot of very good lectures on YouTube. So there are very short series courses of the 10-minute courses of the YouTube, means Python in the YouTube. So I will, if I find it, I will send you the link. Obviously, then I will send you. No, I have taken a course, but from that course I have I learned nothing. So that there is a course that is offered by some in IIT. I have taken some courses in Python, but it doesn't help me that much. And basically I have learned nothing from that course. I means other sources. There are very good. I will send you the lectures. So this is not any certified institute lectures. there some YouTuber just learn YouTuber showing you that how to write means how to learn Python for the beginner. So basically any code means that the how that logic system is going on inside the code. So that is thing. And hmm, hmm, hmm. Ah. Hmm, 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 hmm. Hmm, hmm, hmm. Okay, okay, okay. Hmm. So this is R into. Let's see whether or not it is going from 1 to 3. I'm not. Hmm. Okay, that's why. That's why. Let. Yes, first of all, let us see that the orbit diagram. If you see that orbit diagram, this is the orbit diagram for this not logistic equation. This is the orbit diagram for the for the sinusoidal curve. If that sinusoid, and if you see that this sinusoidal orbit diagram is looking exactly similar to that logistic equation. Let me draw the logistic equation in the lower panel, then it will be more clearer. So okay, so here I have here you have I have shown. First of all, let us see that whether or not Lyapunov exponent curve is showing right or not for the sinusoidal curve. Yes, you see that I'm not writing this. This is not actually for logistic equation. This is for the sinusoidal curve that I have changed in front of you. That, but you see that they are similar. If they are looking the Lyapunov exponent curve and these orbit diagrams looking exactly same, and there is a large window of 3 period. There are period doubling roots of these, so they are looking exactly same. So this hints towards something, that there is something that is not the property of that map, that whether it is sine pi x, whether it is more complicated looking thing, or it is similar, very simple like logistic equation, but if it is goes through period doubling route, there will be something in common in general with this period doubling, or universal thing that is related to the period doubling. So let me, in place of this Lyapunov curve, let me draw this the logistic equation. Suppose I take this y, okay, in the below panel I will okay, in the below panel this is in the below panel I will draw this the orbit diagram for the logistic equation. Let me not share. Suppose, okay, this is the Armin. Okay, let me another thing. Okay, and there will be R values for logistic will be P 2. Let's 2.8 to 4.0, 2.82. Okay. This is not showing. Okay, I don't know why it is not showing. Okay, these are values. Okay, it is, I think it is not showing, but let's forget about that. Let's draw in place of, okay, it's not showing, so there is some issue. I don't know what issue it is, but what I am saying, that there is something in common between them. So let me draw it. Okay, let me draw it then. Let me draw it, then from there we will talking about the Metropolis U sequence. Again, okay, this is the for the sinusoidal curve, and similarly we can get the logistic equations. So logistic equation we have seen previously. So the only difference is that if you see that in the x-axis in the logistic curve, this is was from 0, this is from 3 to 4 or 2.8 to 4. The ultimate was the r value was the 4, but here the for the sin x the maximum values of r is 1. So that is only difference. The only difference between these two is the maximum value. Here the maximum value r is less than maximum value is 1, and here the maximum value is 4. So that means, and if you, so that is the all the things. Now one thing is very common, that is called the Metropolis U sequence, that is universal, which is called the Metropolis. That is universal, which is called the Metropolis U sequence. That is universal, which is called the Metropolis U sequence. That is universal, which is called the Metropolis U sequence. That is universal, which is called the Metropolis U sequence. That is universal, which is called the Metropolis U sequence. That is universal, which is called the Metropolis U sequence. That is universal, which is called the Metropolis U sequence. That is universal, which is called the Metropolis U sequence. That is universal, which is called the Metropolis U sequence. That is universal, which is called the Metropolis U sequence. That is universal, which is called the Metropolis U sequence. That is universal, which is called the Metropolis U sequence. That is universal, which is called the Metropolis U sequence. That is universal, which is called the Metropolis U sequence. That is universal, which is called the metropolis U sequence. So this is called U sequence. What it is, let me. So it is saying something about the order of the periodic orbit. So you see that first periodic orbit is 1 cycle, then 2 cycle, then 4 cycle, then 8 cycle, and it will go like that. So first metropolis U sequence is first 1, then 2, then 2 cross 2, then 8, and first of all and then thereafter a large window of periodic curve will appear, whose period will be 6. So what is the large period? So this is this one. If you see my cursor, then you can point this is how much period is there. 1 2 3 4 5 6. Then metropolis says that after it hits chaos, then again it will show that 6, then 6 into 2, then 6 into 2 to the power 4, then it will go like that and it hit chaos again. Then what will be the large? Then after this is actually the large window. The how much period is there? 1 2 3 4 5. So then metropolis says this is 5, then again 5 into 2 into 5 into 2 square, and similarly this will goes and it will hit chaos. First 1, then 6, then 5, then again if you see what is the large periodic window, that is 3 periodic orbit that we have studied very carefully. 3 into 2 into 3 into 2 square into 3 into something like that, it goes on. Then you will see, means what it is not you cannot observe here, but no, it is actually observable here. Can you see that after period 3 window there is a very smaller 2 windows? So if I try to see these windows, you will see this is the 5 period window. 1 2 3 4 5. So you cannot see from there, but I can see from here, and from 5 to again, okay, hazy, okay, this is the 5, then 5 to again the periodic root 5, then 5 into 2, then you will see here this is then 1, then there will be somewhere which is not visible. Yeah, 4 period, right, exactly, that is the 4 period. But if you it is not saying this is the 4 period, but here you see that there is a negative spike here is a negative spike, negative infinity. So in between somewhere there should be, but it is not visible here, but there should be some period which is actually 6, then the 4 period. You are right that means if you follow this spike, the spikes means that super stable orbit. So since this is a spike, means there is a super stable orbit, so that super stable orbit belongs to 6, then 6, and then again same. Then you are right that 4 into 4 into 2, so this is 4 into 2 square. So this is the metropolis sequence, and you will see this sequence actually follows everywhere where the period doubling is period doubling orbit of chaos appears. So let us see for the case of logistic equation. And it has been experimentally verified that you can okay, that I will show you, okay, that I will tell you later, that values, let me I am drawing for the logistic equation. This is the logistic equation, this is the derivative of the logistic equation. Okay, let me show you. Okay, this is quite long. So it is for the logistic equation. You see, now let's first count. First it will 1, so we know that there is a 1, then 2, then 4, it is quite right. Then the first big period orbit is here, 1 2 3 4 5 6, it is actually right. Then you see there is a large here, 1 2 3 4 5, then there is 3, then there is again 5, then in between somewhere there is some 6 period orbit, then there is 1 2 3 4, then 4 period orbit. So that means metropolis U sequence is can be observed in the logistic equation also. So it is not only here, it is not only here. So there is a experiment which is called the Belzov-Zavodonsky chemical reaction, which is called the Belzov, that BZ equation. It in short, this is called the BZ chemical reaction. And it is quite famous BZ chemical reaction. So in 1982, Simoy et al. In this paper, so Simoy 1952, so in this paper they have studied that in a continuously stirred flow reactor, and found that in a regime in which the period doubling root of chaos appears, and you see in that chemical reaction with the experimental with the order of means with the resolution of the experimental observation, and they have observed the periodic states occurred in the exact order that we are writing here, first 1, then 2 and 4, then it will be chaotic, then again if I increase that steering rate or the flow rate, 6 period orbit will appear, and it will again multiply, and it will become chaotic again, then 5 period orbit appear, then chaos appear again, then 3 period, then 5 period, then 6 period, that they are observed in the experiment. So that you find in this paper. So Simoy et al. 1952. So this is the equation, BZ chemical reaction. So that's all for today. So it gonna quite long lecture. So in the next lecture, here you see it's talking about only order. It doesn't talk about any value that is associated, those things associated with period doubling bifurcation. In the next class we'll see the famous Feigenbaum constant, which is actually associated with this period doubling root of chaos. So we'll see that in the next class, and we will see that there is a method called the renormalization, through which we can predict at which point the first period doubling bifurcation occurs, second period doubling bifurcation occurs, so that we can see from there. So that's it. So is there any question, Subhasaji? Otherwise I can end this meeting here. Okay. So that's why I have right. That's only. Axel. Right. Okay. Hmm. Hmm. Okay. Okay then. Thank you.